A car rental company charges its customers P dollars per day to rent a car, where 60 is equal to or less than P is equal to or less than 150. The number of cars that they can rent per day can be modeled by the linear function N of P equals 750 minus 5P. How much should the company charge per car per day to maximize the revenue? Revenue is the product of the number of items sold times the price per item. In this particular instance, the number of items is defined by the provided linear equation. Therefore, we define the revenue function as, and we write R of P equals P times the quantity 750 minus 5P. Let's distribute the P, then we can simplify the revenue function, and we'll write it as R of P equals 750P minus P squared. To optimize, you must use a derivative test. Let's use the first derivative test here. By the way, the second derivative test is also an acceptable form. Regardless of the derivative test we choose, we always start by finding the critical values. To find a critical value, we compute the first derivative, so the derivative of the revenue function is, and we write R prime of P equals, the derivative of 750 times P is just 750, and the derivative of 5P squared, by bringing the 2 down we get 10, so we would write minus 10P. Critical values are where the x values, or in this instance, the p values, where the first derivative equals 0, or where the derivative is undefined. Since this derivative is a polynomial function, there are no values for which the derivative is undefined. Thus, all we need to do is set the derivative equal to 0 and solve. Setting 750 minus 10p equal to 0, I'll add 10 to both sides of the equal sign. Then we'll get 10p equals 750. Now we'll divide by 10 on both sides, and we get p equals 75. We have solved for the critical value. That is, p equals 75 is a critical value. Now we have to determine if that critical value is a maximum. In using the first derivative test, let's draw a sign chart number line for the derivative. That is, I'll write R prime right above the line and R right below it. I'm going to mark the 75 to indicate that's the function value where the critical value occurs, and where the derivative is, I'll write 0. Let's pick convenient values on each side of the critical value and then evaluate it in the derivative to find the sign. I'll pick 50 for the number to the left of the critical value. When we evaluate 50 in the derivative, we'll get 750 minus 10 times the 50, so that'll be 750 minus 500, and the result is 250, which is a positive number. I'll write pluses to the left of the 75. This indicates that the derivative is positive there. For a value to the right of 75, I'll pick 100. Evaluating the 100 in the derivative, we'll get 750 minus 10 times 100, which would be 750 minus 1,000, and that's negative 250. I'll write negatives to the right of the 75 to indicate that the derivative is negative to the right of 75. Where the derivative is positive, we know that the function is increasing. Where the derivative is negative, we know that the function is decreasing. To say it another way, the function rises up to the critical value and then falls down from the critical value. This shows that by the first derivative test, p equals 75 is indeed a local maximum.